What's up, everybody? Welcome to another video. Hope you're ready to flex those brain muscles, and I hope you're ready to say bye to another semester, because we're headed into finals week and we're going to celebrate that by continuing our final exam review for college algebra. So if you don't have a copy of this awesome review, you can click in the description below. There will be a link. It's over 100 questions, and we are currently on question number 71. So all the timestamps for all the problems I'm doing in this video will also be in the description below. You can click those. And again, I highly recommend trying these problems on your own before watching this video. So don't just play the video and copy down everything that I'm doing. Try everything on your own, and the problems you get stuck on, you can click this video and then click on the timestamps of those problems you're stuck on. Maybe there's some that you don't fully understand how you did it. You can watch those as well. But don't just copy down what I'm doing, because that's not going to help you learn. The goal of these videos is to help everyone learn and prepare for their final exam. So again, if this video does help you, hit the like button and let me know in the comments below. Say, hey, this helped. I like when you did this. I'm always open to feedback, criticisms, all that stuff. And it's nice to know that I help people, you know. I do spend time on this. So yeah, I don't know. It makes me feel good. So let's see, number 71. Let's go ahead and get into it without further ado. Number 71, the population of a country in January 1st, 2000 is 13.7 million, and on January 1st, 2010, it has risen to 15.8 million. So we got a population growth problem. Write a function of this form, okay? I call this P naught. Your professor may call it something else, but I call that P naught. That's the initial value, okay? E is just a constant. It's the number E, right? R we call the growth rate, and T is our independent variable. That's like what we're plugging in for. It's kind of like our X, and this is kind of like our Y, okay? So T represents what? Number of years after the year 2000. So when T is 1, that represents the year 2001. When T is 2, that represents 2002, right? And P of T is the estimation of the population in millions during that year. So we want to find a function of this form to model the population in millions. And then we're going to use this model to predict the population. So a lot of these exponential growth problems go exactly like this, where they give you an initial value, and they basically give you something that you know, and they kind of give you, you can think of it maybe as a point, right? I said T is kind of like our X. So they always give you coordinates that go together, okay? They give you this along with the initial value. Knowing that, we know T, we know P of T, we know P naught. E is just a constant. We can use that equation to solve for R. Right? That's really what we need to know is R. When we get R, we can go back and substitute R back in along with P naught, and then we have a general function. And then we can use that function to estimate at different years just by plugging in for T. So that's the process of how this problem is going to go. So let's go ahead and start. What is our P naught? What is our initial value? And as you can see, when T equals 0, if you want to think of it that way, we have the year 2000. So that's our initial value is 13.7 million, our initial population, okay? 13.7 million, and again, E is a constant, it stays there. R is what I'm solving for. So now I need a T and a P of T that I know, and what it tells me is that in 2010 it has risen to 15.8 million. So again, 2010, 10 years after the year 2000. So my T is 10, and it has risen to 15.8 million. The 15.8 goes here. So now what can I do? I can divide both sides by 13.7 to start the process of solving for R. And if it makes more sense to you, you can write 10R. Same thing. A lot of people prefer, I mean, we're so used to seeing the constant in front of the variable that maybe that makes it clearer. Okay, so divide both sides by 13.7. Start thinking about how we're going to solve for this R. We have an R that's in the exponent. We have a variable in the exponent that we need to solve for. How are we going to solve for this? So I'm going to copy this down. Let's see, 15.8. I'm not going to punch this in a calculator yet. I'm going to wait till the end. That's usually what I do, is wait till the end. This equals E to the 10R. And now I told you to start thinking about it. Hopefully you've come up with the answer, which is we're going to use logarithm or natural log, right? Because that's how we solve for a variable in the exponent, is use logarithm or natural log. And we're actually going to pick natural log, which is ln, because that's the inverse of E. We can actually get rid of the E altogether if we ln both sides, all right? So just remember that. To solve exponentials, you use logs, and to solve logs, you actually use exponentials because they are inverses of each other. Always remember that. So ln of both sides. So again, ln cancels with this E. They are inverses. So I'm left with 10R on the right-hand side. And on the left-hand side, I have ln of this whole thing. So ln of, what is this, 15.8 over 13.7 Now what can I do? Divide both sides by 10. And then I'm solving for my r from here. I just got to punch in a calculator. So these 10s cancel. If I punch this guy in a calculator, I should get 0.014. R equals 0.014. So again, now I know my r and I know my initial value. That was really all I was missing for this function. All I was missing was my r, my initial value. And I was given the initial value. I just found the r. So I have everything I need now. I have p of t equals 13.7 e to the 0.014 t. And now this is a function, right, where t is my independent variable. So we have the function that we need. That's half of the problem done. What's the second half say? Use the model to predict the population in 2012. So 12 years after the year 2000. So that means I'm going to plug in 12 for t, right? Basically, I'm finding p of 12. P of 12 equals, let me go ahead and erase this bottom part too. That's old news. We already found r. Old news. Okay, p of 12 equals 13.7 times e to the 0.014 times 12 up here. So literally all this is do you know how to use your calculator, right? That's what this is testing you on. And if you punch this in a calculator, you will get p of 12 equals 16.3. And again, this represents the population in millions. Million, okay? And that's that. We've done everything we need to do for this problem. All right, number 72 says a veterinarian depreciates a $10,000 x-ray machine. So the last problem was exponential growth. This is going to be exponential decay, right? The word depreciation gives it away. So he estimates that the resale value, which is our function v of t, in dollars after t years is 80% of its value from the previous year, okay? So each year that goes by, it reduces by 80%. Therefore, the resale value can be approximated by this function. It's asking us to find the resale value after 3 years. This is actually a very easy problem. You set up the function, you find the resale value after 10 years, that's v of 3. This problem is really just testing, do you know how to plug into a function? Which hopefully you do. But hopefully you can clearly see why this is depreciation, right? 0.8. Think about multiplying that by itself. That becomes 0.64. Multiply that by 0.8, right? It continues to go down and go down and go down. So hopefully that's clear. But if you punch this in a calculator, let's see, what exactly do you get? 5,120. So that equals 5,120. And then for the next problem, it literally just asks you, what about 8 years? Okay, and round to the nearest 100 this time. So after 8 years, we have v of 8 equals, and we literally do the same thing. So this problem, again, pretty straightforward. Don't let it confuse you. Whoops. Yeah, to the 8th, right? Yeah, 8 years. I almost let it confuse me there. And then if you round, it's going to end up being 1,700. And since this is a word problem, I should put the $sign in front of both these. But again, it could ask you to estimate, to find the year, and they could give you a value that it's worth. And then you would have to use logarithms to solve, right? So they could give you this value, and you have to solve for the t. That could be an option as well. They didn't in this case, but just be prepared to be able to do something like that. All right, number 73. The level of a sound in decibels is calculated using this formula, where I is the intensity of the sound waves in watts per square meter. An electric shaver puts out 0.0001 watts per square meter. How many decibels is that? Okay, so we know the watts per square meter. We're trying to find the decibels. We're given a function. You literally just plug it in, all right? D equals 10 times log 0.0001 times 10 to the 12th. Okay, so you can punch this in a calculator and you get the answer. It equals 80. But maybe you're not given calculator, or maybe you want to see something cool. If you want to see something cool, then what we can do is we can actually change this to be of the form 10 to some power. And then we can combine them. So this is something cool. You can do 10 times log to the, you can rewrite this in, what do we call it, scientific notation, and it would be 10 to the -4th actually. And if you multiply that by 10 to the 12th, you can actually use your exponent rules to combine these as 10 to the 8th. So then I have 10 log 10 to the 8th And then what happens? Log is base 10, remember? That cancels. That's actually just 8. That's how you get the 80. Isn't that pretty cool? So you actually don't even need a calculator for this, which I guess is why they gave it an example. They were hoping you would notice this, but I'm pretty sure this is a calculator exam. I guess I don't know for sure, but yeah, you can punch this in and get the correct answer as well. All right, for number 74, we are asked to find the domain of this function and write it in interval notation. So to find the domain of this function, we need to know the domain of just a logarithm, right? The parent function is how we can think of it. So what's the domain of this guy? Just log x. And maybe you can't remember that, and this is the trick I use to remember. Maybe this will help. So I just remember that the inverse of a logarithm is exponential, right? These two guys are inverses of each other. 10 to the x. These two guys are inverses of each other. That means the domain of this is the range of this, and the range of this is the domain of this. So I can pretty easily just kind of intuitively find the domain and range of an exponential function. And if I can swap those, then I know the domain and range of a log function. So that's how I personally remember, because I know that this exponential, I can plug in whatever I want for x. I can plug in 0, I can plug in a negative, a positive. So I know the domain of this exponential is all real numbers, which means the range of this function up here is that as well. Or we'd write it as negative infinity to positive infinity. What about the range of this guy? Because that's what we're looking for, the domain of a log, which is the range of this exponential. What is the range? Well, can this ever equal 0? This can actually never equal 0. I plug in 0, I get 1. I plug in a negative, it flips to its reciprocal, but it's still not 0. I plug in a positive, it gets bigger. This can never be 0. So the range of this is actually from 0, not including 0, to infinity, which means that that's the domain of our parent function. And since that's the domain of our parent function, we could think of this whole thing like an x, right? Whatever's inside this logarithm has to be greater than 0. That's the main thing you need to remember. If this didn't help you, inside a log has to be greater than or 0. It can't equal 0 or be anything less than 0. So we just take this and we set it greater than 0. 1 minus x greater than 0. I can add x to both sides, plus x plus x to both sides, right? And then I have 1 is greater than x, which means my x, whatever I plug in for x, has to be less than 1, okay? So basically, I'm going from negative infinity all the way up to 1. That's acceptable. And that is the domain of this function. But I found that by setting everything, all the stuff that's inside the logarithm greater than 0, because it doesn't matter what variables, what constant, what's in here, it cannot be 0 or less than 0. So that's how you do it. Set it greater than 0, solve for x, and then write it in interval notation. All right, for number 75, we're going to write this as a sum of logarithms. So you really need to remember your logarithm rules for this exam. So if we have two numbers being multiplied inside a logarithm, we can split that up and it becomes what? It becomes addition, right? We can split that up. If we have division, it becomes subtraction. Okay, and if we have a power up here, we can bring it out in front. So those are the main rules you need to remember, are those 3 rules. So using this rule, we can separate this, right? We can say that this equals log of 1,000 plus log y, all right? And now we can simplify, because it does say simplify if possible. We can simplify, because log has an invisible base 10, right? Invisible base 10. And this is another important rule, actually. I guess it's not really, you wouldn't call it a rule, but this is how you rewrite logarithms as exponentials. And this is very useful. 10 to the x equals 1,000. That's the definition of what this log base 10 of 1,000 means. 10 to what power equals 1,000, right? 10 to what power equals 1,000. So I can simplify this, and it becomes 10 to the third. Okay, 10 to the third power equals 1,000. So that means this whole thing is 3. That means this is 3, right? So I can replace this with 3 plus log y. Log y doesn't change, that's just log y. And this is fully simplified and written as a sum. So we're good to go. All right, for number 76, again, we are expanding this. So these are very common kinds of questions to be asked on a college algebra final, are being able to both expand logarithmic expressions and condense them, right? Combine them into a single term. So you got to go both ways. And in order to know how to go both ways, you got to know your logarithm rules. So please know those. So division, what does it become? Subtraction when I separate it. So I can rewrite this as log. The base stays the same always. Base 7 p to the 8th minus log base 7 q cubed. There's one more step from here, all right? I know it technically doesn't say, but it's always implied anytime you're expanding these that you bring the powers down in front as factors, right? So the 8 comes out in front and the 3 comes out in front, and that's how we leave our final answer. 8 log base 7, and that's just from one of our laws we have that says we can do that, right? You got to make sure you know those laws. Okay, base 7 q. So this will be our final expanded form of this log expression. All right, so like I said, you got to be able to expand them, and you got to be able to go the other way, condense them. You got to be able to swing both ways on this one, all right? So how can I condense this log expression? Well, remember when we expanded it, the last thing we did is we wrote the powers out in front as factors. So going the opposite direction, that's actually the first thing we do, is we bring the factors up as powers, all right? Because you can't start combining stuff while these factors are out in front. That's the cool thing, is we can bring them up and then we can combine them. So log base 5 t to the 4th minus log base 5 u to the 9th minus log base 5 v cubed. And by the way, you can never use these rules if they don't have the same base. So they'll pretty much always have the same base because they want you to use the rules, right? Okay, so my suggestion is to do one step at a time. Combine these two, it becomes addition, and then combine this one, and I'll show you why. So if you combine these two, it becomes, what did I say? I said division, right? Because that's what I meant to say. Comes division. So again, the first one's always on top, clearly. So t to the 4th over u to the 9th minus log, and you could do this technically in one step, but I just see so many mistakes made when students try to do it in one step. And the reason why is because they want to write this on top for some reason. When this is now dividing, which means it's going to end up on bottom. And if you don't believe me, you can take this whole fraction and divide it by this, right? And then you'll end up flipping the bottom and multiplying because you'll have two fractions, and it'll still end up on the bottom. So I guess I can go ahead and do that full process if we really need to. Let's see, just to justify it to everybody why that is. Because remember, this whole thing is the numerator, this is the denominator, okay? So if we want to think of it that way, and I'll just justify why this is the case. This whole thing over v cubed, this is like over 1, right? My parentheses aren't very good here, sorry about that. So when I take the bottom and flip and multiply, I have 1 over v cubed, and it ends up on the bottom anyway, all right? So you can just go ahead and write it on the bottom when you have subtraction if you want, or you can do this each time. It's up to you. So my final form will be log base 5 of, let's see, t to the 4th is up on top. On the bottom is u to the 9th v cubed. And that's it. That's t to the 4th there. And that's it. We have fully condensed this logarithmic expression. All right, for number 78, we are solving this equation. So the first thing I notice is that we already have it in a form where we can solve it right off the bat pretty easily. And what I mean by that is we have to notice that we have log something equals log something. And both of these are just logs, so we have the invisible base 10 down here, right? So the same base, and we have this sort of rule that says log base a of x. If log base a of x equals log base a of y, so basically if you have log of something equals log of something, and those logs have the same base, then that means those somethings are equal. That means x equals y, right? And that's how I'm going to solve this problem, is I'm going to set x squared plus 2x equal to 35. They have to be equal, because the log of this equals the log of this, and this had to be equal, right? So x squared plus 2x equals 35. Now it's just a quadratic. I can get 0 on one side and try to factor and solve, okay? So I'm going to subtract 35 from both sides. I always use the word something to talk about stuff because it can be anything, really, right? Anything can be in the logs for this rule to work, so something usually clicks with students. I don't know why. Using those terms usually clicks. I know that always used to work with me, so. Okay, so now we can factor this. Let's see, two numbers that multiply to be negative 35, that add to be 2 plus 7 minus 5. Boom, there we go. X plus 7, x minus 5 equals 0. That means x plus 7 equals 0, or x minus 5 equals 0. So my two solutions are negative 7 and 5. But what do I have to do? I have to be real careful with problems like this. I have to go back and plug each one of these in and make sure they work. Always remember this, because remember, The domain, whatever's inside this parentheses, cannot be 0 or less than 0, okay? So -7, when I plug it back in, I get 49 minus 14. That's still positive. We're good. And when I plug 5 back in, I get a positive. So we're good. Both these solutions work, all right? And I can write them as a solution set. X equals, use the curly brackets here. But always go back and make sure, because a lot of times you'll end up throwing out one of your answers because it won't work. That's just what happens with logarithms. So always go back and check. All right, so there are two main strategies you'll use to solve equations like this, to solve logarithmic equations. One is what we just did, where you can get log something equals log something, then you can set those things equal to each other and solve. Two is what we have to do for this, because we can't actually get log something equals log something. The reason why is because this constant, this is messing us up. But what we can get is log something equals some number. Okay, and if we can get that, then we can rewrite it as an exponential equation and solve it pretty easily. So we're going to have to use our log rules to combine this, and then we'll have log of something equals some number, which is 3, right? So addition becomes what when I combine it? Multiplication. So I have log base 3 of r times r minus 6. That has to distribute. So this is how I would write it personally. When I distribute that, I get r squared minus 6r. So log base 3 of r squared minus 6r equals 3. And how does this work? Do you remember how to rewrite this? I remember it by drawing arrows. An arrow to this guy here, and then an arrow back to what's inside the log. So I can rewrite this as 3 to the third power equals r squared minus 6r. 3 to the third power is what? 27. So I have 27 equals r squared minus 6r. This is a quadratic. I have to get 0 on one side and try to factor. So if I subtract 27 from both sides, and I'm just going to go ahead and erase this because they cancel, and write 0 just to save me some space here. Subtracted 27 to both sides. So I have 0. So now I can try to factor this. Let's see, what can I break this down into? Two numbers that multiply to be -27 and add to be -6. -9 and +3. I think that's what's going to work. So I have r minus 9. And again, to check your answer, what do? You just FOIL it back out. If you want to check your answer real quick, make sure you factored it right. So that means r equals 9 and r equals -3. So I'm going to go ahead and write my solution here. R equals 9, comma, -3, because again, I set each piece equal to 0, right? This is equal to 0. That means this equals 0 or this equals 0. I solve for both. But again, remember what I have to do. I have to go and plug these back in. Actually, clearly this -3 doesn't work. It makes that negative, and that's not defined. We can't have a negative inside a log. So I have to cross out that -3. Let's make sure the 9 works. Positive, positive, we're good. So actually our only solution here is r equals 9. And that's why I say you always have to go back and check. Especially when you have logs that turn into quadratics, most of the time you end up throwing out an answer, okay? So always go back and check, and in this case our r equals 9. That's our only solution. All right, number 80, another word problem. If we have $36,000, it's invested into account earning 5.9% interest, compounded continuously. Determine how long it will take the money to quadruple. Round to the nearest year, use the model A equals P times E to the RT, where A represents the future value of P dollars invested at an interest rate R, compounded continuously for T years. So don't freak out about the formula. You'd be like, I've never seen this before. It's okay. All it is an exponential equation, and it's going to be exponential growth because interest accumulates, right? So we're given $36,000. That's what is invested. That's our P, all right? So $36,000, that's our P. That's the amount invested. E is just a number. What is our R? 5.9%, so that's written as 0.059, right? You always write the percent as a decimal, 0.059. All right, and does it give us a T, or is that what we're solving for? Determine how long it will take money to quadruple. So the T is what we're solving for. So that means we have to have an A. What is our A? Let's see. How long will it take the money to quadruple? So A is quadruple this 36,000. So if I can do some quick maths here, I think that's 144,000. 144,000. So what we can do is solve for T. We're going to use a natural log, right? Hopefully that's clear. We have an e, we have a variable in the exponent. We're going to end up taking the ln of both sides, but first we need to get rid of this 36,000. And actually what's cool is we know that this 144,000 is quadruple this. So we already know that this is 4, right? These cancel, that's 4. 4 equals e to the 0.059t. Now we ln both sides. ln, that cancels with the e. Let me draw an arrow here. What do I have now? ln of 4 equals 0.059 times t. Divide both sides by 0.059, and ln over 0.059, that's going to be my solution for t. So when I punch this in a calculator, I should get like 23.48, and it says round to the nearest year, so I'm going to round down to 23. So it's going to take approximately, let's see, t is what does it represent? T years, so 23 years. 23 years. Okay, for that to quadruple. That's quite a long time, but quadrupling is quite a big increase. So yeah, 23 years. All right, for this number 82, we are solving this system of two equations. And specifically, we're solving for x. So we can use substitution or elimination. Either one would work. I tend to lean toward elimination just personally, so I'm going to use elimination. That means I want to eliminate the y's because I'm solving for x. So I can multiply this top equation, both sides by 5, and both sides of this bottom one by 2, all right? And then I'll have positive 10y and negative 10y, and I can combine and cancel. So if I take the top equation down here, and I multiply everything by 5, I get 5x plus 10y equals 0. And then if I take this equation, the second equation, and rewrite it and multiply everything by 2, I get 6x minus 10y equals negative 66. All right? Now I do my elimination. I just add down 11x. My y's are gone. 10y minus 10y, that's gone, equals 0 plus negative 66. So if I divide both sides by 11, I get x equals negative 6. And if it asks to solve the system of equations, typically you'd go back in and substitute it back in, and you'd solve for the y, but in this case it actually just asks for the x, so we are done. All right, number 83, another system of equations. We can solve it using any method, but it says if a system does not have one unique solution, state whether the system is inconsistent or whether it's dependent. So an inconsistent system has no solution. So you'll end up with something like this. 0 equals 2, something that clearly isn't true, doesn't make sense, it's nonsense. That means it's inconsistent, meaning there's no solution, meaning these lines are parallel, they never intersect. That's what it means graphically, right? Dependent means you'll get something like this. 3 equals 3, something like this, where it's always true, right? 3 equals 3, always. So that means they are dependent, and graphically that means they are the same line. They are layered on top of each other. So just a quick review of that, and I do have a video on systems of equations if you want to check that out. Let's see, so we need to start with the process. I'm going to use elimination because I can just multiply this top equation by what? 8. And if I multiply that by 8, I get 32x plus 8y equals 24. And you can probably see what's going to happen now. This is gone. This is gone. I have 0 equals negative 3, which is nonsense. So this is an inconsistent system with no solution. All right, number 84, we have another word problem here. And this one, I'll be honest, is pretty tricky. So hang in there. We'll see if we can get through this one. A student borrows a total of $4,800 in student loans from 2 lenders. Bank 1 charges 4.5% simple interest, and Bank 2 charges 5.9% simple interest. She is not required to pay off the principal for 3 years. However, at the end of 3 years, she will owe a total of $782.40 for interest from both loans. How much should she borrow from Bank 1? So what we have is 2 relationships. We have this $4,800, right? We have the total amount of the loans. And then we have this relationship that has to do with the interest rate, okay? So basically we can take each one of those pieces of information, form an equation out of each one of those, and then solve this like a system of equations. So really the hard part about this, the hardest part is going from English to math, all right? But let's see if we can make some sense of this. So we need to name some variables. So Bank 1, this is the amount borrowed from Bank 1. We're gonna call this X. And the amount borrowed from Bank 2, we're gonna call that Y, all right? And we're trying to find X. That's what we want to solve for, is the amount borrowed from Bank 1. So we know that this total is 4,800, right? This is the total amount borrowed. So this is kind of the easy equation. The tricky one is the other equation, the 782.40. So that's the total interest owed, 782.40. But how do I get this? We probably know it definitely has to do with the interest rates, all right? And what happens with that 4.5% interest is if you multiply 4.5% by the amount borrowed, that's the amount interest paid in 1 year, okay? But we're going 3 years, so we need to take that and multiply by 3, right? So we have 3 times 0.045, 45x, plus 3 times 0.059y. So again, the 0.045x, that is the interest paid in 1 year from a loan from Bank 1, but we're going 3 years. And then this is for Bank 2 for 3 years, and this is the total interest. So now we have a system of equations that we could solve this. I know the numbers are really ugly, but we can solve this. And probably what I would do, actually definitely what I would do, is elimination. And you can make this a little easier, in my personal opinion. There's a trick you can do to get rid of decimals, because decimals are the real ugly part, right? You can multiply everything by 1,000. That's what I would personally do. So you don't have to do this. You can punch this in a calculator, punch this in, and then do some kind of elimination. But I know we're solving for x, so I don't know. I'm just going to multiply this by 1,000, because what it does is it shifts everything over 1, 2, 3 decimal places, and I have no more decimals, right? So I don't know. I like that. So if I multiply everything by 1,000, I get 45 times 3. That's 135x. 135x plus 59 times 3, what is that? 177y equals, and again, I just shift over 3 decimal places, so this is 782,000. So this is a big number, but I still think this is less ugly than decimals, in my opinion. So I multiplied everything by 1,000. Now I can multiply everything up here by -177 and set this here and do my elimination, right? I think it's a little bit easier. So -177x, and you could have done a substitution too if you would have preferred that. You could solve for, let's see, you'd solve for y, and then you'd substitute that in. That works too. I just tend to prefer elimination. So -177y equals, let's see, what is this times -177? I need to find that out. All right, so I have -849,600. And now if I add down, I cancel the y's just like I wanted to. These can combine, and I get negative, what is that? -42x. -42x equals, these can combine, let's see, 782,400 minus 84,9,600. -67,200. Now I can divide both sides by -42. Obviously my answer is going to be a positive. Alright, so -67,200 divided by -42 is going to give me 1,600. So the amount borrowed from Bank 1 is 1,600. And again, there are several different ways to do this. You could have done substitution. You could have done a different elimination. You didn't have to multiply by 1,000. There's lots of different ways. This is just the way I like to do it. So yeah, that's the way I'm showing. Do it whatever way works for you. As long as you get to this 1,600 answer, then you're good. All right, number 85, we have a system of equations we are solving. This time we have 3 equations and 3 variables. So these problems can be long, they can get tedious and get a little crazy, but the process is the same each time. So I'm going to go through the process, and I think on this one the numbers are going to get pretty crazy, but the process is the same. If you have big numbers, small numbers, it doesn't matter. If you know how to do it, you know how to do it. So yeah, let's go ahead and start. So what I do is I label these 3 equations, A, B, and C, all right? So we have A, B, and C. And then we're gonna basically combine these two and these two, and we're gonna come up with D and E. And what we want to do is eliminate the same variable. So if I combine these two and eliminate x, then when I combine these two, I want to eliminate x as well, okay? So then I'm left with two equations with two variables. Then I can do a substitution or elimination again and end up with, let's see, DEF, equation F down here, and that'll be a single variable. I can solve for that variable, and then I can basically backtrack. Come back to here, solve for that variable, come back to here, solve for that third variable, then I have all three variables. The problem is I may not directly be able to come to here, right? And the reason why is because I can't cancel anything as is. I can't do any kind of elimination. I have to multiply some stuff, right? I have to multiply some stuff, and then I can do an elimination. So this is the tedious part, like I said. So what I would probably do here is I would multiply this middle one by 6, and I would combine those. And then I would multiply this middle one by maybe a -3. So I have a -3x here and a +3x there, and combine those. So again, I could take any multiple of any one of these equations and add it or subtract it to another to combine them, right? You can think of it that way. So if I combine these two, what I'm really doing is I'm taking C plus 6 times B. If you want to think of it that way, you can. That kind of makes sense to me. But yeah, that's what I'm going to do. So I'm going to rewrite B, but times 6. So maybe I'll write 6B here. All right, that's supposed to be a B. Sorry about that. And then I'm going to rewrite that down here. -6x. Let's see, so 6, that's a -48. 6 times 8, 48, yeah. Minus, that's going to be 54z. Everything's getting multiplied by 6. 24 times 6, what is that? 120, 144? Yeah, -144. Cool. All right, so again, these are the two equations I'm going to add. I'm going to add these together, and this is going to form my D. We'll call this D when I add these together. So I'm going to, since I don't really have room over here, I'm going to write the D down here. So I'm putting the D right there. I'm going to add down, so that becomes 0. Then I add down, that becomes -52y. I told you these numbers get crazy. I'm sorry. I'm going to have to figure out what I'm going to do with this board, how I'm going to even have room for all this. Negative, let's see, what is that? 47. -47z equals, if I add these, I get what? -151. All right, so now I have my D. Now I need my E. So I combined C and a multiple of B. Now I need to combine A and B somehow, okay? And that's going to give me my E, equation E, all right? So what can I rewrite? I rewrote 6B here. Maybe I'll erase that, and I'll rewrite, you know, either A or B in a certain way, because again, I can't just add these and do elimination. I have to multiply by something first. Sometimes you even have to multiply both equations by something. I don't think we do in this case. I think we can take, this time we can take -3b, all right? And the reason I do negative is because I know I said we can add or subtract any of these, and we technically can, but usually we think of it as multiplying by -1 and then adding. That tends to confuse students less, because a lot of times when they subtract, I don't know, I've just seen more mistakes that way. So I'm going to relabel this as -3b, all right? And if I find -3b, then I can combine that with A, and that's going to be my E, if that makes sense. So remember how I drew the arrows here? Bam, bam. So that's still what we did. We just had to multiply by stuff, all right? That's still what we ended up doing. This was the D. That one was the D. This one ended up being the D. This one's ended up being the E, okay? So hopefully you're still with me here. So let's see. -3b, I'm going to rewrite this. And that gives me 3x, which makes sense because the x is what I'm trying to cancel. Let's see, -3. I get plus 24y plus 27z equals, let's see, -3. That gives me +72. So now, again, I'm combining this all the way up there with A, so it may have made more sense to write it up here. I'm just worried that that's off the screen and that y'all can't see. So just make sure I'm covering these up and I'm combining this with A. So that's going to give me my 0. It's going to cancel my X there. Plus 24 minus 7, that's plus 17. That's 17Y. All right. Let me double check that. Yeah, we're good. 27, that's 32 plus 32Z equals, let me make sure we're on the same page here, that's going to be 66. I think that number looks familiar, so I think I'm on the right track. I worked this out before because I could tell it was going to get crazy. All right, so now I have my D and E, so now it gets even more crazy, and the reason why is because I need to eliminate one of these variables, right? Substitution is going to give me crazy fractions. I don't really want to do that. Elimination is going to give me huge numbers. There's just no way around it. You have to get ugly with it. So again, if I do elimination, I can combine this or this. I don't really see one being easier than the other. And if you're ever confused on what to multiply by, I can multiply this by 52 and this by 17 and combine the y's. That will always work. You can always just multiply this by the bottom number and the bottom by the top number. Sometimes there's a smaller number that works if they share a common factor. In this case, 17 is prime, so that's actually the only number that works. I'm not sure if something else works for these, but I'm just going to go ahead and stick with that. I'm going to stick with that. So I need to do 52 times 17. Let's see, I'm going to have my calculator handy for this problem. 52 times 17, so 884. So again, I'm multiplying D by, let's see, I'm multiplying D by 17, and I'm multiplying E by 52, all right? So D is getting multiplied by 17. So let me see, if there's even room down here, is there going to be room down here for these? So if I write it small, 17D and 52E. Can we see down here? Okay, so 17D is going to give me, let's see, 52 times 17, that's negative 884. Let's see, since I'm multiplying by, I am multiplying by a positive, that's staying negative. Then I need to do 47 times 17. Yeah, there's really no way around this. It's a shame that this is a problem on here. I feel like they should have gave something that was nicer. But I guess you got to be prepared for the worst. I don't expect something like this to be on the final, if I'm 100% honest. But I cannot speak, I can't say anything guaranteed, but I would be surprised. That's all I'm going to say, is I would be surprised. So times 17, times 17, times 17. And if there's a better way to do it, let me know in the comments. And please do it that way, you know. Let me know. I'm always open to being wrong or to there being a better way. So again, this is y. I'm missing the y because this is going to be positive 884y. That's why we multiplied by those numbers, because those are going to cancel. What is 32 times 52? Right? I'm multiplying all this by 52. That's plus 1164. No, 1664. Plus 1664. Z equals, what is 66 times 52? That is 3432. Now I can combine these and get my, let's see, D, E, F, right? I've taken a multiple of D and a multiple of E, and I can combine them to get F. So let's see, do I still need my calculator? I might to do some of this addition. So if y'all can't see down there, let's see, where can I write F? Maybe over here if I write it small. So when I combine these, I get 0, I get nothing for y, but then I need to do 1664 minus 799. I probably could have done that in my head, 865. So 865z, hopefully y'all see, these cancel. I get 1664 minus 799, that's 865z. I'm gonna write this over here, 865z equals, and I do this math here, it's gonna be somewhere around 900, maybe 800. Let's see, 3432 minus 2567, 865. So z equals 1. So I did all that, all those crazy numbers just to find out that z equals 1. So now is when I can start solving. This is the fun part, because now I can backtrack. Since z equals 1, I can plug that into either of these equations. I'm going to pick this one, all right? I'm going to pick this one. Again, we use f. This was our equation f. Let's see, where's my red marker? this was my equation f, and I can't hold them all at once. I'm going to use black for that one. This is my equation f. We use that to get one of our variables. We solve for one of our variables. Then we backtrack. Then we can use d or e. I could use either of these, actually. These are just bigger numbers. So I'm going to use this. I'm going to replace this z with 1 because that's what z is. So I'm going to end up subtracting 32 from both sides. I get 66 minus 32. So I get 17y equals 34 if I do this math where I subtract 32 from both sides. If 17y equals 34, I'll write it up here, 17y equals 34. If I divide both sides by 17, that gives me y equals 2. So I have z equals 1, I have y equals 2. Now I can solve for x. I can go back here. Let's see, it doesn't matter which one I pick in this case. I'll pick this one. This is 2. This z is 1. So now I have, let's see, where do I have room for this? Maybe up here, can y'all see up here? 6x minus 8 plus 7 equals negative 7. So let's see, minus 8 plus 7, that's minus 1, right? And if I add 1 to both sides, I get 6x equals negative 6. X is going to equal negative 1. 6x equals negative 6. X equals negative 1. Hopefully y'all followed me on that. I told y'all, I warned y'all that this is going to be tedious and these numbers are just ridiculous. I worked this out beforehand. I could not find a better way. 17 is prime, 47 may even be prime. I can't really think of any factors. I mean, this is a rough example, but if you get the process, you start with the 3 equations, you combine, right? You eliminate one of the variables, then you combine those, you eliminate another, and you get down to 1, and then you backtrack the whole way. So this is how you do it. I'm sorry the problem isn't better, but let me know if you want to see a better example. I can pull one up on the internet. I can make a separate video on it, and one with nicer numbers that I can keep more organized and that sort of thing. But yeah, I apologize. I'm just working through the review. Like, that's what, you know what I mean? That's what this video is about. So here's number 85. So our last example with number 85, we had one unique solution. It was a consistent system and independent because we had one unique solution. This time we are asked to determine if there is a unique solution, we need to find it. If there isn't a unique solution, there may be infinitely many, and then we call it a dependent system. Or there could be no solution at all, then we call it inconsistent. All right, so the process is the same. We still have our A, B, and C. We combine, we reduce, we get down to one variable. If we have something that's one unique solution, then we end up with something like x equals 2, z equals 5, right? Something where we solve for a variable. If we end up with no solution, then we end up with something that's nonsense. 0 equals 2, something that's never true. If we have a dependent system with infinitely many solutions, we end up with something like 2 equals 2, 5 equals 5, right? Something that's always true. So those are the 3 cases. But again, you still have to go through this process and get to the end to fully find out. At least at this level of college algebra, that's the best way to find out. So I'm going to go ahead and start. And again, these problems are hard to do on a whiteboard that's not like super big. I'm sorry, because I got to rewrite a bunch of equations and do crazy stuff. So I'm doing my best. I'm doing the best. So let's see. I'm going to multiply this by 3 and this by 2. And I'm going to get rid of the x's. If I multiply, well, technically one of them I need to multiply by a negative. So I'll rewrite, let's see, I'm going to combine 3a with negative 3b. And when I combine those, that's going to give me my A, B, C, D. That's going to give me my D. All right, so D is going to be down here. All right, let's go ahead and rewrite these and combine. So 3a is negative 6x plus 9y minus 9z equals 6. Okay? What about negative 3b? Then I get 9x. Wait, why did it have negative 3? That should be a 2. I'm tripping. Negative 2, right? Because I want to multiply by the other number. This one by 2, this one by 3. So negative 2b. And I get 6x. And then what else do I get? Negative 2. That's going to become plus 4. So plus 4y. That's going to become minus 4z equals, let's see, negative 2, negative 26, all right? So what happens when I combine these to get my d? Remember, my d forms from these top two, and that's exactly what we're doing. We just took multiples of each one, which is fine. We just have to make sure we use these two and then use these two. But we can use whatever multiples we want. Okay, hopefully everyone gets that part. This is 0. This is 13y. This is negative 13z. See, these numbers are way better. I don't even need a calculator. Negative 20. Now I have my d. All right. Now I'm going to use b and c, but I have to eliminate x again. I'm going to find my e, equation e, right? So I'm actually going to erase here and rewrite whatever multiples of b and c I need to use and use those to, I think this is the most organized I can get as far as on the whiteboard. So I have e down here, e. This is what I need to find. So again, e is this one here. So I can combine multiples of these two. And in fact, I'm going to take the top one times 4 and the bottom one, I'm going to take b times 4. So 4b. Let me call them by their names since I named them. 4b and 3c. Let me make sure that's right. There we go. Yeah, because that's going to get rid of it. They're going to both become, let's see, negative 12 and 12, right? So here we have the negative 12x. Let's see, 4b. That becomes minus 8y plus 8z equals 4. So that's 52. All right, 3 times c. We have 12x plus 21y minus 21y equals times 3, negative 72. Now if I combine these, I get my e. What do I get? That becomes a 0. This becomes a 13y. Oh, I see what's going to happen here already. This becomes a minus 13z. And this equals what? When I add down, what do I get? Negative 20. All right. So now what if I multiply the bottom by negative 1 and then add? Or I could think of subtracting. I end up with something like this where it's, let's see, I'll multiply the bottom by negative 1 and then I'll add. That's what I like to do. So negative, positive, positive. All right. So I get 0, 0, 0. 0 equals 0 means we're dependent, right? It means we have infinitely many solutions. So that's what we get, is we get 0 equals 0, which is something that's always true. So that means our system is dependent. We have infinitely many solutions for x, y, and z. So we'll write dependent system. All right, for number 87, we have solved the system of equations using the substitution method. So this really should be some relief from the kind of problems we've been doing, because this one is very quick and straightforward, right? Using substitution. So basically I isolate either x or y, and then I substitute that back into the other equation. So hopefully it's clear which one I'm going to use, right? I'm going to solve for either this y or this x, because I don't want to mess with these squareds, all right? I don't want to have to square root things, and that's ugly. I want to mess with this y and this x. So I can just add x to both sides, and then I can use that y. So if I take this and I add x to both sides, I have y equals 9 plus x. And since y equals this is how my substitution works. Since y equals this, I can replace this y with this 9 plus x. So once I do my substitution, I have x squared plus y squared. Where's my y? My y is 9 plus x. So 9 plus x squared equals 81. Now I don't even have any more y's. I only have x, right? That's the goal of this, is you want to eliminate the y, only get x. That way you can solve for x, right? So I have to FOIL this out. Don't make that mistake of distributing the square. The biggest mistake, if you do that, a kitten dies, all right? Don't do that. You don't want a kitten to die. So x squared plus, this has to be FOILed out. You can do that off to the side if you want. 9 plus x times itself, right? That's what the square means. So that becomes 9 times 9, that's 81, plus 9x, plus 9x, that becomes 18x, right? We combine our like terms, plus x squared. So I get x squared, I'm just going to kind of arrange and combine the like terms, plus x squared, plus 18x, plus 81 equals 81. I can combine another like term here. This is 2x squared. So I have 2x squared plus 18x. And then what else happens? This is a quadratic, so I have to get 0 on one side. And what's cool is when I subtract 81 from both sides, that's gone and that's gone, right? So I just have 2x squared plus 18x equals 0. And I actually am going to end up with two solutions for x because I can factor out the 2. All right, let me factor out the 2 out in front. I have x plus 9. Actually, I can factor out a 2x. That's what I meant to do. Sorry about that. The 2x, because that's the common factor. There's your factor of 2 and a factor of x. And that's what I meant to do. I just didn't do it. But I caught my mistake. As long as you're going slow, you can catch your mistake as you do it and immediately correct it. So I took out the 2x, and I want to check my answer, because lately I've been making mistakes. So let me check my answer. 2x squared, 18x. I get right back to where I came from. I'm good. So if this equals 0, then that means 2x equals 0. All right? So I can set up two different equations. 2x equals 0, or x plus 9 equals 0. So if I solve each of these equations, which I'm sure y'all are all capable of doing, I get x equals 0, and I get x equals negative 9. So I actually have two solutions for x, which means I'm going to have a y coordinate that goes with each of these x's, right? So my solutions are going to be kind of like ordered pairs. I'm going to have xy and another xy. So what is y when I have x equals 0? I can use this equation. So y minus 0 equals 9. That means y equals 9. So here I have y equals 9. And this is one pair, right? What about when x is negative 9? I have y minus negative 9. I may need to write that out. That might be less easy to see. So that becomes y plus 9 equals 9. Okay, that means y is 0 here. Y is 0. So my solution, you list it as coordinate pairs, and I actually want to draw this so everyone can see why we have two solutions. Remember what a system of equations is? It's the intersection, right? It's where these intersect. This is the equation of a circle with radius 9 centered at the origin, all right? I don't know if you've seen or remember the equation of a circle with radius 9. So this is a terrible circle, but this radius is 9 and we're centered at the origin. This is y minus x equals 9. If we rewrite this, I erased it earlier, but we have y equals x plus 9. So we have a y-intercept of 9 and a slope of 1, right? Rise over run is 1. So our y-intercept starts here, and since we have a slope of 1, we're coming up this way. So we're intersecting twice. At this point here and this point here. Is that what we got as our answer? X equals 0, y equals 9. That's this point. X equals negative 9, y equals 0. That's this point. So if we draw this out, this is just the radius, by the way. This isn't a line. I was just showing the radius. If we draw this out, it lines up with our solution. So our solution set is 0, 9 as one coordinate. As one coordinate pair, sorry. And then negative 9, 0. But hopefully that makes sense, is that you can draw it, because that's what all these systems of equations mean. You can always graph them, and you can think of them as when these lines intersect, or curves, whatever they are. It's really tricky with 3 variables though, because then you have to picture it in 3-dimensional space. It's not really effective to graph them at that point. But with stuff like this, you can, because this is linear. We know how to graph that, and this matches the equation of a circle. And it's kind of cool to see. I don't know. It's kind of cool to be like, oh, okay, yeah, they intersect, and to check your answer, yeah, I don't know. So one more problem, then we'll end the video. All right, number 88. We are solving this system of equations. We have 2 equations, 2 variables. This time we have an x squared and an x term. So this is the first example we've seen like this. But we can use any method, substitution or elimination. So actually both will work in this case. If you wanted to use substitution, you could substitute basically y for y. So since y equals this, you can set this equal to this. If you want to do elimination, you probably need to multiply by -1 and then add. That would work as well. So that's what I'm going to do. I'm going to multiply, and I'm just going to do it without rewriting it. Negative, negative, positive, negative. I just changed the signs of everything, multiplied everything by -1. That way when I add down, this becomes 0. And the reason I like that, the reason why it's kind of a shortcut, is because this becomes 0 and we have a quadratic that we're solving, right? And since we're solving a quadratic, we already want it to be equal to 0. That's how we solve it. So it is kind of convenient. It is a little bit of an issue though. Well, I guess not really. To have the negative out here, we can get rid of that easy, but let's see. So that becomes negative x squared minus x squared. That's negative 2x squared plus 22x minus 56. So I can think of this 2 different ways. I can factor a -2 out in front. That's probably what I'm going to do. or I can multiply both sides by -1/2. Because the 2 is irrelevant as far as this solution. Whether the factor of 2 is in there or not, my solution is for x when it equals 0, right? You already know. So I'm just going to factor it out in front. So -2 comes out in front. X squared minus 11x plus, this is what, 28? And remember, if you want to double check your answer, plug it back in. Boom, boom, boom. And you can see how it doesn't affect it, because this equals 0. I'm going to end up factoring this, and that's what's going to give me my zeros here. And it has nothing to do with the -2, so that's kind of cool. I don't know. Let's see. How can I factor this? 28, two numbers that multiply to be 28. Multiply to be 28, add to -11. 14 and 2 doesn't work. 7 and 4. 7 and 4 if I do minus for both. Minus, minus. So I have -2, x minus 7. Yeah, that's going to be x minus 4. If you want to check your answer, you'll be good. But this gives me x equals 7 and x equals 4. So again, I have two solutions, and they're both going to be coordinate pairs. So I'm going to go ahead and actually just write them as coordinate pairs. 7 for this x coordinate, and I'll leave the y coordinate blank. And 4 for the x coordinate, I'll leave this y blank as well. So I can go back and plug into either one of these, all right? So plug in 4 and 7 to find my solution. So let me do that side work down here. And let's see, maybe I can do it, I can go back to the original. I'll erase that. I'll erase that. I'll make that a negative, and I'll make that a positive. All right, I'll go back to the original because it's a little easier to plug in for. So 4 squared, that becomes 16. I'm finding the y coordinate that goes with this 4. So that becomes 16 minus 4, that's 56, plus 42. Let's see, 16 plus 42, that's 58. Minus 56, that's positive 2. What about the 7? 7 squared, that's 49. Minus, what's 7 times 14? That's a big number. 98? 98? Minus 98 plus 42. Let's see, 49 plus 42, 91 minus 98. That's -7. So these are my solutions. And if you want to know why we have two solutions, kind of like we drew a picture in the last case, we can draw a picture again. And it's because look what we have here. We have an upward and a parabola that's opening up, right? And a parabola that's opening down, okay? So when they intersect is going to be something like this. A parabola that opens up, a parabola that opens down. They're going to have two intersection points, right? Bam, bam. So, I mean, visually you can see that why we have two solutions here, but that's kind of cool to see. But yeah, these are our two solutions, 7, -7, and 4, 2 for this system of equations. All right, that's going to be it for this video. We got through 88 problems on this review. There's about 20 left, and I'll be honest, I'm not sure if I'm going to get to those last 20. So if there's something you really want to see from those last 20 questions, let me know in the comments below. But yeah, I promised my pre-cal students I'd make a video or two to help them review for pre-cal, and also have my own exams. I got to study for my own exams. I can't fail my classes because I'm making brain gains videos, you know what I mean? So I got to take care of that. But if you enjoyed the video, please hit like. If you have questions, leave comments below. If you appreciate what I'm doing, let me know in the comments too. That's always nice to hear. And keep flexing those brain muscles. Good luck on your final exams. I know y'all will all kill it, and I'll see y'all in the next video.